All right, here we are, lesson 4.1, just taking a look at the concept of gravitational forces, and we're going to be focusing specifically on gravitational forces due to the Earth, most often because physics is done near the Earth as far as we know. So, first of all, when we're defining a gravitational force, we're really talking about an attractive force between any two objects due to their mass. Due to their mass. Okay, so that would be any two objects with mass. So that would be, let's say, you with your desk, or you with your pen, or more specifically, usually we're talking about a celestial body, and the closest celestial body that we have is the Earth. So when we take a look at this concept checked here, which diagram best represents the gravitational acting on you and on the Earth? I'll give you 2 seconds thinking about that. Okay, do you have your answer? The correct answer is in fact B, and that is because it is an attractive force, and here we see an attractive force between the two. They are equal in size because, as Newton's laws state, for every action there is an equal and opposite reaction, and so the fact that you are attracted to the Earth actually means the Earth is just as attracted to you. However, the Earth will move a lot less because the Earth is a little bit more massive than you are. I know that this diagram kind of suggests otherwise. However, that is not the case. We're usually not that size compared to the Earth. Taking a look here now at the concept of weight. Weight is simply a force due to gravity, or a gravitational force, so force due to gravity, on an object. Right, so whatever gravitational force that has, the object has, that is its weight. Now, we should specify this is by a celestial body. We're not going to worry about, for example, the attractiveness between you and the pen in your hand, or you and the device that you're looking at, because it is so much more insignificant compared to your gravitational force between you and the Earth. There is a big difference between gravitational weight and mass. Mass is just the amount of matter that we have, where weight is the actual gravitational force acting on it. Now, these are used interchangeably because a gravitational mass is just a mass measured by comparing it with the weight of known masses. So it's a mass measured by comparing the weights of known masses. And usually that's just like a balance beam idea, where if I've got an object here and I put, several masses here to balance them out, and I know the mass of each of these is 1 kilogram, then this object here would be 3 kilograms compared to that one. So 3 1 kilogram masses would have an equal weight to this object. Therefore, we calculate this object to have a 3 kilogram mass, even though we calculated it by the weight, as these two weights are the same. Now, gravity does act as on a distance. It's an action as a distance force, which means even though the objects aren't touching, you still feel them. And you know this because anytime you've dropped something, the gravity still works even though it's not in direct contact with the Earth. Some other examples of action at a distance forces other than the gravity could include, for example, a magnetic force. Right? You have two magnets, they will act on each other even though they're not in contact with each other. Or an electrostatic force. Right, where you have picked things up or moved things due to static electricity, even though they are, even though they're not in direct contact. And all of this is mostly because we kind of take that action at a distance as being in a field, which is really just a fancy way of saying a 3D region of influence. And a gravitational field will just be a region of influence around an object with mass. Right, where you can also have magnetic fields and electric fields, but a gravitational field is specifically due to an object's mass. So, continuing on, gravitational field strength. If we take a look at a gravitational field strength, how strong is that gravitational field? Well, that's just really the gravitational force per unit mass in the field. So this would be the per unit mass of the test object, not the celestial body causing the object. So mathematically, that would be looking something like this. Okay, where this mass here is in fact a test mass. But one of the things, if we think about gravity, it does in fact act at a distance everywhere, but the further away we get, the less strong it is. Although the further the objects are, the less strength everywhere. Although the further the objects are, the less the strength. The relationships between a gravitational field strength, which we symbolize with this G, and the distance between them, and we're going to use R for that because it is a radius. It could be in any direction, so it could be between here and here, or here, or here. This distance is the same, and so we use R representing a radius. This is actually an inverse square relationship, meaning that the further you get out, if you double the distance, it's not just half as strong, it's actually going to be less than half as strong. So we write G is proportional to R squared. So if I double the distance, I have 1/4 of that gravitational field strength. If I triple the distance, I have 1/9 the gravitational field strength. We can see this here that on the surface of the Earth, we've got a specific gravitational force, and when we get to twice, we're 1/4 of that. When we get to a third, we're now 1/9 of the distance. 1/4 will be 1/16, and so on. So let's just to finish off here. If we were to, let's say, what if the radius were to decrease by a factor of 4? Well, if we say that G is proportional to 1 over R squared, that R squared is now 1/4 of what it was before, which means our G nu will be 16 times as strong. What if R were to increase by a factor of 2, so we're doubling the distance there? Well, again, G is proportional to 1 over R squared, which means our G nu is going to be 1/4 that of what it used to be. Well, what if the test mass doubles or the test mass is half? Well, this is actually going to have no effect. And the reason for that is because it is the test mass that we're changing here, which will change the force acting on that test mass, but it doesn't change anything about the object generating the field. Okay, this does not generate the field. Okay, thank you for watching, and if you have any questions, please ask your teacher.